Building on our previous discussion about the relationship between sensation and behavior, we now delve into how the very structure of mental order is established. We're moving from what sensations are to how they get organized into the rich tapestry of experience we perceive. Think of it as moving from individual threads to the loom that weaves them into a pattern. All right, let's start with the raw material, incoming nerve impulses or afferents. Imagine a newborn brain, or at least, conceptually, a brain before it's learned much. The first time a specific combination of stimuli hits, say, light and sound together, the corresponding neurons haven't met each other yet. They don't have those little handshakes, those connections, based on this simultaneous arrival. So, that initial impulse doesn't know its place in the grand scheme of things. It's just a signal. But then, every time that same light and sound combo occurs, maybe a bit later, maybe a bit differently, these neurons start to interact, reinforcing each other, forming a tiny connection. It's like laying down a single brick. Do it again, add another brick. Over time, with countless such encounters, you build a wall, a network. Each neuron, through these repeated linkages, starts to find its neighborhood, its functional role within the larger CNS city. It gains meaning not because it's inherently red or loud, but because it consistently shows up with certain other signals. Now, here's where things get tricky. We say these early connections create qualitative distinctions. Red looks different from blue. But calling this initial process experience feels wrong, doesn't it? Like saying a baby's first cry is already an emotional experience. This early linkage stage isn't about conscious feeling or perception in the way we usually mean it. It's more fundamental, almost pre-psychological. It's the machinery being built, the factory floor being set up, long before any product's sensory qualities are made there. Using experience here is misleading because it implies a richness and subjectivity that isn't there yet. So to keep things clear and avoid confusion, we need a different word, a neutral term for the basic wiring up based on what happens together. And that term is linkage. Simple, direct, physiological. So what exactly is this linkage? Think of it as the most fundamental, lasting impact the outside world can have on the brain's wiring. It's not about understanding or meaning in the moment. Imagine a dog hearing thunder and lightning simultaneously. Initially, the thunder sound and the lightning flash might just be two separate sensory events. But if they always happen together, the brain starts linking the neural signals representing them. The lightning flash signal now carries a hint of the thunder sound signal, even if the thunder isn't there. This linkage prepares the organism for future situations where thunder might predict lightning, or vice versa. It's learning a predictive association, a discrimination, before the organism can consciously say, aha, thunder means lightning. These linked events don't need to be conscious experiences. They're just physiological signals getting wired together. Why not just use the word impression? It sounds similar, right? Well, impression has baggage. It screams mental experience, subjective qualia. That's precisely what we want to avoid talking about at this foundational level. Linkage is cleaner. It focuses purely on the physical process. Event A happens, event B happens, and now the brain has a stronger pathway connecting the signals for A and B. It also explicitly ties memory back to this idea. Remembering something is essentially recalling a complex pattern of linked physiological events. So linkage is our chosen term for this core mechanism. This brings us to a big debate. How does memory work? There's a common idea, sometimes called the storage theory, which is surprisingly influential. It suggests that when you have an experience, like seeing a cat, a little picture of a cat gets stored in your brain, and later, when you recall the cat, you retrieve that picture. It implies some kind of special mental substance or storage container. Our view based on linkage challenges this. We argue that there's no known physical mechanism for storing discrete mental images or entities. What the brain stores, or rather what it builds, are connections between the physiological events representing the stimuli. Memory isn't a filing cabinet of pictures, it's a complex web of linked pathways. Any theory trying to explain mind physically needs to embrace this linkage view of experience and memory. So, how does this linkage business relate to the actual colors, sounds, and textures we experience? Well, the emergence of a specific sensory quality, like the color red, depends on prior linkages. Before red became red in our experience, there must have been linkages forming between the light signals hitting the retina and other signals, perhaps related to objects, contexts, or other sensory inputs, that consistently co-occurred with that type of light signal. Even once a basic system for classifying these impulses is built, it's not static. New experiences, new linkages keep tweaking and modifying this system. Think of it like refining a map, you keep adding new roads and landmarks. However, as the map becomes more detailed and complex, adding a single new dot becomes less likely to drastically change the overall layout. The system stabilizes, but it's never truly finished. What's the big takeaway here? Every single sensory experience you have, whether it's tasting coffee or hearing music, is happening against a backdrop of pre-existing linkages. These linkages, forged by past interactions with the world, shape how you interpret the present moment in ways you're often unaware of. They're like invisible filters or lenses, constantly adjusting your perception. Crucially, this ordering of sensory qualities isn't fixed. It can be subtly changed by new linkages, even ones that don't consciously register as a new experience. This has huge implications for how we understand knowledge and perception, which we'll circle back to later. This focus on linkages formed by external stimuli naturally leads to the age-old debate, nature versus nurture, or in academic terms, nativism versus empiricism. Is our perception of the world innate, hardwired, or is it learned, built up from experience? For individuals, it's probably a mix, hard to generalize. But the key question here is broader. Can the entire system of sensory qualities be seen as constructed by the organism's history of interaction with its environment, the effects of the external world shaping its internal connections? Our answer is a resounding yes. We lean heavily towards an environmentalist or empiricist view for the formation of this sensory order. The world builds the map. Now you might think, hold on, this sounds like pure empiricism, building everything from scratch. But doesn't Gestalt psychology argue against reducing complex perceptions, like seeing a whole face or a melody, to simple elements? And you'd be right, there seems to be a tension. However, the author argues that maybe the Gestalt critique doesn't fully apply here. Why? Because our theory doesn't just say elements build Gestalt qualities. It says all qualities, both the basic ones like red and the complex ones like the Gestalt face, ultimately trace back to this initial pre-sensory linkage process. It's not about building higher-level structures from lower-level ones in a purely additive way, but about the entire structure emerging from the ground up through these fundamental linkages between non-mental elements. It's a different flavor of empiricism. Okay, let's visualize this. As these linkages form, the resulting network of connections starts to mirror, however imperfectly, the relationships between the external stimuli that caused them. It's like the brain is creating a map of the world, not in geographical terms, but in terms of which stimuli tend to appear together. This map doesn't capture the physical identity of the stimuli, just their statistical associations. Remember how science classifies things? We classify stars based on their observed properties like brightness and color relative to each other, not necessarily assuming they're all identical objects. Similarly, the brain classifies stimuli based on their relational patterns within the CNS. Our job now is to explore the kind of map this process creates. So this mental map evolves gradually. And crucially, this gradual evolution means the brain's internal order slowly approximates the actual order of the external world. Now, traditionally, people thought perception was direct and immediate, while thinking was abstract and reorganizing fixed elements. But our view flips that. We argue that even basic sensory perception involves constant reclassification, just like thought. Both rely on the CNS actively sorting and resorting information. It's all part of the same ongoing effort. The brain's microcosm, striving to reflect the macrocosm of the external world, constantly refining its internal map. But let's be realistic, this mental map is far from perfect. First off, our senses aren't in perfect cameras. Receptors are selective, You can't see ultraviolet light or hear infrasound. And sometimes, different physical things stimulate the same receptor in the same way. Think about how a red apple and a red shirt might look similar, even though they're different objects. Also, the types of stimuli you encounter depend heavily on your specific environment. A desert animal's mental map will be shaped by sand, heat, and cacti, not snow and pine trees. So the map reflects the local landscape of stimuli, not necessarily the global picture. It gets worse. Our internal world matters too. Signals from our body's internal state, our hunger, our temperature, our fatigue, constantly feed into the CNS and influence how we link external stimuli. Plus, the brain's wiring itself isn't perfectly uniform. Some pathways are easier to form than others due to anatomical constraints. Imagine trying to build a road network where some areas are hilly and others flat. The resulting map will be distorted. Finally, remember the hierarchical processing? Lower levels do a rough classification, and higher levels classify those classifications. Each step adds potential distortion, like interpreting a blurry photo of a sketch of a scene. The final map is a complex, potentially warped reflection of reality. So let's stick with the map analogy, but with caveats. The network of connections in the brain acts like a map of the external world, but it's a very rough, dynamic sketch. It captures some relationships, sure, but it's missing details, distorting perspectives, and constantly being redrawn. It's not a static atlas. It's more like a traveler's constantly updated, sometimes inaccurate, hand-drawn map of the territory they've explored. Now, if everyone's brain is building this map, how similar are they? Well, because we all live in somewhat similar environments and have similar evolutionary histories, our maps will share broad similarities. You wouldn't get lost using someone else's map of Paris, even if it's a bit old or simplified. But are they identical? Absolutely not. Your unique life experiences, your unique brain wiring, mean your map is subtly different from mine. And since both our maps are constantly changing, the chance of them being exactly identical at any given second is practically zero. Thinking about similarity between these dynamic, non-identical systems is philosophically tricky, but the map analogy helps grasp it. We can still understand and use different maps of the same place. One crucial point about this mental map: it's not about spatial distance. It's a topological map. Think of a subway map. The lines show connections, routes, but the distance between stations on the map doesn't reflect real-world distances. What matters is the pathway, the connections. It tells you how to get from A to B via C, not how far apart A and B are. It's about the structure of relationships, not the geometry of space. The simple map analogy starts to break down when we consider the brain's hierarchy. It's not just one flat map. It's more like a stack of maps, each representing a different level of processing. Lower-level maps might represent basic shapes or movements, while higher-level maps integrate these into more complex concepts. The lower maps act like local guides and filters, deciding what information gets passed up to the higher maps, which in turn provide context for the lower ones. It's a layered system of partial maps working together. Where does consciousness fit in? The highly detailed conscious sensory experience we're familiar with seems to happen mainly in the highest levels of this hierarchy. But even in the lower levels, there's clearly some classification going on, guiding reflexes and simple behaviors, even if we aren't consciously aware of it. We can infer a simpler rudimentary version of our sensory order exists there, based on how organisms respond unconsciously. This leads to a fascinating idea. The difference between purely mechanical processes and mental processes might just be a matter of degree. How complex is the classification and ordering involved? The more complex, the more mental the process feels. Let's shift gears slightly. We've talked about how linkages build the static map. Now, let's look at what happens dynamically within that map. When a new stimulus arrives, it doesn't just trigger a simple reflex. It interacts with the existing state of the brain. Think of it like dropping a pebble in a pond that's already rippling. The brain isn't blank slates, it has an ongoing activity, a background hum representing the recent past and the current situation. Higher brain centers use this ongoing state, combined with the new input, to decide how to respond. It's like having a short-term memory buffer constantly active. Imagine each incoming signal branching out like a tree, influencing many other signals along the way. As these signals travel up the processing hierarchy, they keep branching, influencing more and more neurons. This means the brain's overall state becomes increasingly dependent on the lingering echoes of past stimuli, rather than just the latest input. It's like the brain's background music is getting louder and louder compared to the new song starting. The existing pattern of activity, the pre-existing distribution of impulses, starts to dominate how the system responds. So, what's the main job of a new stimulus in these higher centers? Increasingly, it's not to trigger a direct action, but to tweak the overall mood or readiness of the system. It's like setting the stage for future actions. The stimulus adjusts the brain's disposition, making it more likely to respond in certain ways to whatever comes next. The classification becomes more general, less tied to specific outputs, and more about maintaining a flexible, adaptable state. Think of it as a central control panel constantly being adjusted by minor inputs, rather than directly flipping switches for peripheral devices. This whole dynamic process, the interplay of ongoing activity and new inputs, creates a kind of internal representation, a snapshot of the current situation. This internal model allows the organism to orient itself, to adjust its responses appropriately based on the context provided by this internal representation. It's an orientation apparatus, constantly updating its view of the world to guide behavior. Here's a fascinating consequence. Even after the original stimulus stops, the brain might keep circulating the associated signals for a while. It's like the echo in a canyon persists after the shout. Why? Perhaps because the signals representing that moment's entire sensory scene reinforce each other in a loop, creating a persistent trace until a new stimulus breaks the cycle, signaling that the situation has changed. This persistence allows us to perceive objects as stable even when our eyes move, or to maintain a sense of continuity in our experience. It's a complex interplay of reinforcement and inhibition among linked impulse groups. We need to be precise here. There are two kinds of memory traces or representations. First, there's the permanent-ish wiring, the map we discussed earlier, the structural changes in connections. Second, there's the fleeting pattern of active signals at any given moment, the model of the current situation. Think of the map as the city's infrastructure, and the models as the traffic flow on that infrastructure at a specific time. The current pattern of active impulses, the model, is what allows the brain to interact with the immediate environment. Let's hammer this home. The map is the static infrastructure, the connections, the pathways, the categories the brain is capable of using. It represents the organism's history, the types of stimuli it has ever encountered. It exists whether or not anything is currently active. It's the potential, the framework. The model is the dynamic pattern of activity within that framework at any given moment. It represents the current situation, the specific stimuli present now. It's the actualization, the manifestation of the framework in action. So the map provides the categories, the grammar. The model provides the sentence, the specific meaning derived from the current input, constrained by the grammar. The map determines what kinds of things the brain can talk about, but the model expresses what it's talking about right now. The model is dynamic, constantly shifting, always dependent on the underlying map structure. The map sets the rules. The model plays the game according to those rules. Therefore, the complete orientation system isn't just the map, it's the map plus the current model displayed on it. It's a model within a model. The significance of the current situation model comes from its position relative to the overall map structure. This allows for incredibly nuanced responses. The same stimulus might mean something different depending on the current context, which is captured by the interplay between the map and the model. To make this clearer, think about board games. In a Kriegspiel, you have a map of the battlefield, and you place figures on it. The pattern of figures relative to the map tells you the strategic situation. Or consider Nine Men's Morris. The position of the pieces only matters in relation to the board's pattern. Now imagine flexible blobs moving through a network of tubes. New blobs enter from afferent tubes. Where they go depends on the pressure from blobs already there. The pattern traced by the moving blobs within the fixed tube system is analogous to our dynamic model within the static map. The significance lies in the relational pattern, not absolute position. Another analogy: think of a complex geometric shape like a fractal. Its essential properties can be described by mathematical equations. But you can describe it using different coordinate systems: Cartesian x, y, z, polar r, theta, phi, etc. The equation defines the shape, but its appearance changes depending on how you view it. Similarly, the significance of the impulse patterns in our model isn't about their absolute spatial arrangement, but about their relationships defined by the underlying connection structure, the map. Just like the equation defines the geometry regardless of the coordinate system used. Finally, let's tie it back to association. The constantly changing pattern of active impulses, the model, is meaningful precisely because it tends to evoke other impulses. This is the core of associative learning. Seeing a red light evokes the signal for stopping. Hearing a bell evokes salivation. Each element in our mental model is a node in a vast web of associations, constantly triggering chains of related impulses based on past linkages. Meaning arises from these connections. That wraps up our look at how the brain builds its ordered world through these fundamental linkages and dynamic models.